Okay, so I must. You see my screen, right?
Yes.
Okay. So let us now. I will repeat what we already said in the previous lectures quicker. Okay. So you will have a resume of our previous two lectures. So we started with an energy, a deformation energy. And this deformation energy is given as the integral over the reference configuration of W function of F d volume. So W is the volumic energy, deformation energy density. Okay. And we introduced the external potential. We have also called EX in this form. It has to be a linear functional on placement. Okay. So in general, this is a linear functional of the placement. Then this assumption is related to our idea that in the actual configuration, every material particle of our continuum body, for instance, is subjected to a force, weight force. So you have a force depending on mass density rho and g, the gravity acceleration. And it is very well known that a material particle under gravitational force has potential this scalar quantity. Here you have the inner product between the gravitational force and the placement. And in this way, you calculate the component of placement with respect to the direction of the gravitational force. So this is a kind of hint about the expected structure of some external interactions potentials. So linear on placement. These kind of potentials or external loads are called dead loads. Okay, this weight is a kind of dead load. Okay. And then we asked ourselves, which kind of dead loads can we apply to the deformation, to a body having this deformation energy? When you integrate by parts, the expression for the first variation of deformation energy, this is the first expression for deformation energy. Then you integrate by parts, and at the end, you get that this expression is equal to the integral over C star of div dw over df with sinus mine dot delta k plus integral on the boundary of C star of dw over df dot n dot delta key. I'm using this formula in hiding the indices, but if we need, we can write them component-wise. And here you have d over dxa. So this is the divergence. And this inner product is Eulerian. So you have the saturation of these two indices. Similarly, here n is Lagrangian, delta K is Eulerian. So these formulas you can immediately transform into component-wise formulas. Okay, this calculation is important for two reasons. One, you get strong formulation for equilibrium. Okay, but also you learn which kinds of external loads you can apply. Why? Because delta of the total energy, which is equal to the delta of deformation energy plus delta of external, the energy, the potential of external interactions, has to be equal to 0. So as we said last time, if I introduce an external concentrated force, so I imagine to have a material point x bar, and I consider this external interaction. So I imagine to have one point and a force applied in one point, okay, and the potential relative to this expression is given by this minus. You remember this minus is needed because if you have that your body is the minimum of energy must be falling towards the weight, okay. So if you have one concentrated force in one point, and you write this plus that, you have that the first variation of deformation energy is a volume integral plus a surface integral. So you have volume integral plus surface integral plus the first variation of this calculated in one point equal 0 for every delta T. So if I take with the standard argument, localization argument, delta key concentrated around X bar, this, as usually, as we said, I repeat once more, I take a sphere of radius epsilon centered in X bar. Okay, the volume, this volume integral goes with epsilon cube. If you are in the interior, this integral on the surface is 0. If you are not in the interior, you are on the boundary, this surface integral goes with epsilon square. So when you calculate the limit for epsilon tending to 0, you are left only with f of x bar dot delta key x bar equals 0 for every delta key x bar. And this is an apparent paradox, because at the end, we prove that the external force is 0. So why this apparent paradox has to be considered? Because when you impose that the first variation of total energy is 0 for every virtual displacement, and this is your equilibrium condition, clearly the kind of external actions which can be applied to your body having your fixed deformation energy is determined by the kind of deformation energy you have chosen. So we can conclude that first gradient continua, I call first gradient continua those for which W deformation energy volume density depend only on F. This is an assumption. This is an important assumption. So for first gradient continua, you can have only volumic and surface dead load concentrations. So now, if you remember, we have spoken about, and this is the moment to go back to this point, we have spoken about the table made by every healthy philosopher of science. Here you have the mathematical objects, and here you have the physical objects. So our theory, let us say first gradient continuum theory. Okay, the objects of our theory are displacement key, the deformation energy W as a function of F. Then these are the kinematical descriptors. Then kinematic descriptors, and this deformation energy is a constitutive equation. Then you have the principle of minimum energy. You apply this principle to the kinematical, to the model you are considering. You prove some theorems and you get some conclusions. For instance, no applicable concentrated forces on a point. Okay. Here you have Galileo beam, for instance, with Galileo dead load. Okay. And you have some phenomena, the deformation phenomena you have. Okay? You cannot conclude that you cannot conclude concentrated forces does not exist. First of all, concentrated forces, not concentrated forces, forces are a mathematical object. Therefore, they exist. Period. Forces are covectors on the space of displacements. That's all. And a statement about a mathematical object, by the way, there is nothing which is measured directly linked to forces. Think about this. Don't believe to the propaganda of some presumed practical people who talk about forces as if they were existing in real world, okay? Or as if they were immediately intuitive objects. Forces, you know, D'Alembert said that forces are obscure. Nobody understands really what is a force. Think about it. If you have a dynamometer, so you link a weight to a dynamometer, and you claim that you are measuring a force, what are you actually measuring? You are measuring the elongation of a spring. Elongation is a mathematical object immediately linked to a physical quantity. Then you need a theory. For instance, you need to know that the force is linked, the intensity of the force is linked to the variation of length divided to the original length divided by the original length of your spring, and then measuring these, you get information about the force. Okay, so forces are a mathematical object, are mathematical objects playing a role in a mathematical theory. Okay, so sometimes you hear statements like in physical reality, there is no concentrated force. Actually, if you zoom in, you have instead of having one force concentrated in a point, you zoom in and you see that you have a volume distribution of force. But as this radius is very small, then you are a bad physicist. You write the equation as if these forces were concentrated in a point and things like that. Then somebody who studied engineering, after you have heard that concentrated forces are not existing, they teach you that you can apply a force in a point of a beam, and you must solve the problem of the deformation of a beam under an applied force. And you ask yourself, why here I can use concentrated forces and here I cannot? The answer is, I start giving you this answer. The answer is easy. When you have 3D first gradient continuum, okay, the deformation energy is this one. You calculate the first variation. So this is a purely mathematical reason. You build integration by parts and you get integral over C star of div dw over df dot delta k with a minus sign, and then you have plus integral on the boundary of C star of dw and delta k. So the first variation of these deformation energy is the sum of a volumic and surface terms. So delta E def plus delta E ext equals 0 has a meaning only if E ext is integral of minus B dot key on the volume, B volume, plus integral on the boundary of C star of B sigma minus dot key on the surface. So this is a volumic integral and this is a surface integral. So mathematically, in our model, we can introduce only forces per unit volume and forces per unit surface. This is a mathematical situation. Okay? So the total energy is given by integral over C star of WF, the volume, plus integral over C star of minus B volume dot key d volume plus integral on the boundary of C star of a surface density of force dot key the area. This is the admissible expression for total energy in the case of first gradient continua. And you find these words clearly written in Piola's works in 1848, for instance. Now, what is rather astonishing is that many engineers confuse the mathematical reality with the physical reality. So first of all, they confuse math with physics. Okay, and then second, they believe that only first gradient continua may exist. They conclude there are not concentrated forces in reality. Okay. Why I am underlining to you this? Because if the deformation energy depends on F and grad F, then you can have line forces on the boundary. And this is a personal story. I had a lot of academic battles because people claimed that line forces on the boundaries are not existing. I mean, I think that everybody, if you go in the history of science, you find this situation repeated systematically, because the confusion between mathematics and physics, and to believe that your hypothesis is generally valid. So, in this context, never believe that this is the only possibility. This is not true, okay? In general, every mathematical model is based on assumptions. Okay. Now, once we have established which kind of external loads you can apply to a first gradient continuum, so this is a particular assumption, let us try to understand some consequences of our assumptions. Okay, we can call the consequence I want to discuss today the theorem of Piola about balance laws. So our assumption, our hypothesis is, the list of our hypotheses are: W depends only on F. Okay. Actually, W of F is equal to W bar of C of F, because the deformation energy depends only on C. You remember, C, we discussed a lot, is F transpose F, and it is 1 when you have a rigid placement, and when it is not 1, then you have a deformation. So we assume that the deformation energy depends only on the deformation measure. Okay, then we have a meta hypothesis, which is an hypothesis more general than this, the principle of minimum energy. Okay, then we make calculations and we find that div dw over df plus b volume equals 0, dw over df n equal b sigma, and essential boundary conditions are verified by key. We have that this is a necessary condition for equilibrium. And we have called this the strong formulation of equilibrium equations. Okay. Now, to solve this problem is I'm not talking. I will give you the statement of the theorem later. So I'm simply now recalling what we already said, what we already deduced. Okay. Now, if you remember, we needed to introduce constraint forces. Okay. We state that you can replace the essential boundary conditions with suitable external forces. So the idea is the following. Imagine that you have a body. You block this body here, and you apply on the free. You remember, we divided the boundary of C in the boundary, the part of the boundary where you gave essential boundary conditions, and the free part of the external boundary. Here you give, here displacement is given. Here you assign B sigma. Okay? So we can remark that external world can interact with C star in two ways. With forces or blocking some material particles. So we have a kind of Dr. Jekyll and Mr. Hyde, okay? We have apparently we have two different entities, two different mathematical entities, forces and constraints. Now, Lagrange could prove the existence of constraint forces. Remark, no uniqueness. Okay, to give the mathematical details of these, it is rather involved. I think that we will, if we find the force, we will try to do this after you have seen how COMSOL works in some practical problems. So we will be helped by your numerical experience. I have discussed with Erden about if it was useful to jump this part of the mathematical presentation or not, and we agreed that it is better if we skip the mathematical part for the moment in order to have the flow of our discussion go without too much disturbance, okay? Okay, so the existence of constraint forces can be stated as follows. We can replace essential boundary conditions with suitably chosen surface forces without changing the equilibrium configuration. So in a sense, it is an equivalence. Instead of imposing the displacement here, this is the reason for which we can talk about Dr. Jekyll and Mr. Hyde. Dr. Jekyll is the essential boundary condition. Then Mr. Hyde is the forces per unit surface, which I can replace to the essential boundary conditions without changing the equilibrium of our body. So you can imagine to have applied there some forces per unit area, and these forces per unit area have exactly the same effect on the deformation phenomena as the essential boundary conditions. Okay, the forces giving exactly, we can also call equivalent forces. These equivalent forces are called constraint forces. Okay, so you have our body in the actual configuration now. On this body, you have B sigma applied on the free part of the boundary. Then you have B sigma constraint. Sorry, we wrote in the other way, so let's write them in this way. And then you have dB volume. And we have our equilibrium condition. dE dot equal integral over, you can write with a change of variable, you can write this either in the reference or in the actual configuration. So you have integral over C star of dW over dF delta F d volume plus integral over C star boundary, over C star of minus B volume dot delta key plus integral over the whole boundary C star of B total sigma delta key. And this has to be equal to 0 for every delta key. So I wanted to, let us say, it was considered useful for calculations, and you will see soon why, to replace essential boundary conditions with constraint forces. Okay. Now, we made last time some calculations which are correct. We will go back to this later. Now I want to give you some extra details, but when delta key is the rigid motion infinitesimal displacement, okay, and this is what we have seen recently, delta key is equal to delta U0, a small displacement of 1 point, plus delta theta, a small angle, a small rotation vector x minus x0, if we want to write this Eulerian, okay, and dW over dF delta F is equal to 0. Why this? If you have that W depends only on C, so if the deformation energy depends only on the deformation and it is 0 when you don't have deformation, then this first variation has to be 0. Okay? In a rigid motion, there is no deformation energy. This is an assumption. So I have shown you the mathematical counterpart of this statement, but let us proceed. We accept this. It is, by the way, our theory must be built in this way. You want a deformation energy which in a rigid motion is 0. Otherwise, it is not a deformation energy. So, once more, if you have that for every x in a certain set, the property P of x is true. So when I say that for every human being, he has 2 eyes, okay? When I consider the particular class of human beings coming from Turkey, whatever some of our politicians may claim, okay, they also have 2 eyes, okay? There is no racial group which is not enjoying the properties of human beings, okay? So if I have a subset S of X, for every S belonging to capital S, P of S is true. Somebody here could tell me why you are giving these basic logics again and again. Because my past experience, I told already to you that I have a book of my grandfather who was a lawyer. This book was printed in 1906, and exactly this rule is explained for high school students. I mean, this is a basic argument for every human activity based on rationality. Okay, but why I'm repeating this to you? Because even great scientists, I will not tell you the name, when I wrote this equality for every delta key, and then I applied it for a specific delta key, a class of rigid body motions, they told me, are you studying then only rigid body placements? I mean, this equality is true for every variation of placement. So I have my equilibrium. Okay? With the externally applied forces and essential boundary conditions. Then I replace essential boundary conditions with constrained reactions. Okay, then I say I am in an equilibrium configuration. Okay, if I change a little bit the shape of the body, this quantity must be 0. If my variation of shape is a translation or a rotation, still this quantity must be equal to 0. However, in the particular case of rigid placements, displacements, this quantity is equal to 0. So I have that for delta key equal delta U0 plus delta theta vector x minus x0, integral, instead of writing the integral on C star, I do a change of variable and I write in the actual configuration. I have integral of C star of B Eulerian let's call it with B tilde in the Eulerian configuration, because you must change delta V star and delta C star into delta V and delta sigma. Okay, but let's go postpone the technical details later. Delta K, delta V, dV plus integral over the boundary of C of B tilde sigma dot delta K delta area. This has to be equal to 0. So this is a necessary condition for equilibrium. Okay? So, can we expect that the result obtained out of this necessary condition can give us back the minimum of energy or even this equality? We cannot, because we are considering only a particular subclass of delta keys. Which subclass of delta keys? Non-deforming delta keys. So we are testing equilibrium. You remember, when we test equilibrium, when we test minimality of f of x in the neighborhood of f of x0, and we write Taylor expansion, we consider a small variation of the independent variable, and we test if the value of the function is increasing or not. So I vary a little bit the independent variable. How do I vary a little bit the independent variable? Considering a generic delta key. For every delta key, the energy must increase if I am in a stable equilibrium. Okay. In particular, if I consider rigid displacements, the energy must increase. Okay. And as the stationarity conditions says that the first variation of total energy must be 0, because of the hypothesis about the deformation energy, this delta E thought in this particular case is given by this expression. Okay, now let us write delta K equal delta U0. So we assume that delta theta is 0. Okay, and I write integral over C of B tilde dot delta U0 plus integral on the boundary of C of B sigma dot delta U0 has to be equal to 0. So I can take out of this integral delta U0, okay, and I can write integral over C of B tilde plus integral on the boundary of C of B tilde sigma. This is equal to 0 for every delta U0. Okay? If I call this the resultant force applied to the body C, I find as a consequence that in equilibrium configurations, the total resultant force is vanishing. And this is the first cardinal equation for dynamics. And you find the first proof of this statement for continua in Piola's works around 1828. Of course, Euler wrote this for beams, for rigid bodies. So Piola stated it for continua, exactly following the reasoning which I developed up to now. Now we have that, therefore, integral of B volume dot delta K plus integral on the boundary without C star of B sigma dot delta K is 0 now for every delta K equal to delta theta vector x minus x0. Okay. So I place this expression here and I find BV dot delta theta vector x minus x0 plus integral over the boundary of C of B sigma dot delta theta vector x minus x0. And this is equal to 0 for every delta theta. Okay. Now, I hope that you remember this fundamental property of vector product and inner product. This quantity is equal to the quantity obtained by commuting in this way the order of factors. So you have B dot C vector A. This is a standard equality in vector algebra. And you could not survive to any class in electromagnetism without understanding, without checking this equality. So if you accept this, you get integral over C of, I place this at the beginning. So x minus x0. Sorry. Delta theta. Okay. Dot x minus x0 vector BV plus integral on the boundary of C of delta theta dot x minus x0 vector B sigma. And this has to be equal to 0 for every delta theta. Okay. Now, delta theta is not depending on the point on the integration variable. So at the end of the story, we find that integral over C of x minus x0 vector BV plus integral on the boundary of C of x minus x0 vector B sigma has to be equal to 0. This is the cardinal equation for dynamics. And this also has been found for rigid bodies by Euler and for continua by Piola. Now, probably you have understood why now we know why the concept of moment of a force has been invented. Historically speaking, it is certain that the concept of moment of a force has been invented making this calculation. So calculating the work done by the total forces applied to a physical system while calculating the first variation of total energy and imposing equilibrium conditions. So the remark, now we will do this calculation because I am worried that maybe you never have seen it. So the moment of the system of forces F with respect to the reduction pole x0 is defined in this way. Okay, now what happens if I change x0? All our reasoning, if you remember, rigid body motion, you have the choice of one point. You represent the virtual rigid displacement of x like x0 plus u of x0 plus delta theta vector x minus x0. So one could say, if I change and I represent the rigid displacement with respect to another point, what happens? Okay, you have that this formula becomes like that. You have x minus x0 prime plus delta theta vector, and you have x0 prime minus x0, because if you factor x0 primes minus plus simplifies. And you can remark that this is ux0 prime. So you have that your formula does not depend on the choice of the pole. Okay. Similarly, if you have the moment of F with respect to x0, you have that this is equal to the integral of x minus x0 vector b sigma, b volume, plus integral of x minus x0 vector b sigma. you can make the same trick. So you write integral of x minus x0 prime plus x0 prime minus x0 vector b volume. I will not write this because it is exactly the same stuff. And then you have integral of x minus x0 vector bv plus integral of x0 prime minus x0 vector bv. And this is plus integral of x minus x0 prime vector b sigma plus integral of x0 prime minus x0 vector b sigma. Okay? Now, this is m f x0 prime, and this is what you can take out of the integral this vector, which is constant, and what you get here, you have integral of bv, integral of b sigma. So this is the resultant force. So you get that the moment changes with the pole with this formula, and remark the similarity of this formula with this. Of course, you can change the sign here. You know, you can change the order of the vector product. Okay, let us write in the right way so the similarity appears even better. If you change the order and you change this order, you get exactly the same thing. So I have changed this order, I get 1 minus. Then I change the order in the vector product and I get another minus. So this formula is still true. And then you remark the obvious similarity of this equation with this equation. So the structure of the variation of the moment with respect to the pole and the virtual velocity in a rigid motion have the same structure if you replace this, we have called delta u 0 prime. If you replace the moment with the displacement and the resultant with the rotation. Okay. Why these properties are important? Because clearly, if R of F is 0, then MF x0 equal MF x0 prime. So, imposing the first, this one, the first cardinal equation for dynamics. So if you know that it is true, then you write the second cardinal equation for dynamics. The moment is equal to 0. Okay, you don't need to specify, to choose in a particular way x0. You can choose it as you like, because all these moments are altogether 0. Of course, don't be clever And don't play one pole and here another pole, because then the formula is not anymore invariant. So you must change the pole systematically in your formulas. Okay. So what we have proven: equilibrium as in an equilibrium configuration as determined by the principle of minimum of energy. We have the resultant forces are zero, the resultant force is zero, and the resultant moment is zero. And this is a necessary condition for equilibrium. Okay, so we have some minutes, and I want to use these minutes with some comments. You could ask me why you are so sure that these conditions were obtained as a consequence of minimum of energy. Okay? Now, go in every old book. Do you know how they call the condition RF equals 0? They call it equilibrium with respect to displacements. And they call MFX0 equals 0 equilibrium with respect to rotations. So if you go and check every book dating between 85 and 1950, you find always these conditions called equilibrium with respect to displacements and equilibrium with respect to rotations. So it is clear that they were invented using the reasoning which I gave you now. Okay. Now, an important warning. We are tired. So, imagine to have a beam. Okay? And imagine that somebody is asking you to solve this problem. Find the equilibrium shape of a beam when you have a concentrated force in one point. This is for sure a problem that everybody who studied engineering has learned to solve. Okay. Okay. Why we can talk about a concentrated force in the theory of beam? I tell you why. Because the deformation energy is given by this expression. So you have the second derivative of transverse displacement U appearing in the deformation energy. We will go back to this point, to this argument. So in the theory of beam, you can apply concentrated forces. Why? Because in the deformation energy, you have the second derivative. You remember, this is the curvature of the beam. If I have a beam and I'm curving it, the second derivative is changing, and to deform a beam having a change of curvature, you need to give a deformation energy to it. So the deformation energy depends on the integral of the second derivative square. Okay, I must place the bracket in this way. I write it in a clear way. And this is a line integral along the length of the beam axis. Okay, so I can tell you a nice story. In the theory of beam, you can calculate sometimes the constraint reactions. Why? You say, I write a free body diagram for my body. I place here the force of externally applied force. Then this clamping device is exerting a force and a torque, a moment. Okay, I don't want to draw in this way. Then, so I have reaction 1, reaction 2, moment. I don't want to make the calculation. We have no time now. So what I do, I write balance of forces and moments, because I know that in equilibrium, the resultant force is 0 and the resultant moment is 0. Okay. And if I'm lucky, I can calculate this and that constraint forces. Okay. So this is a trick, very useful. The theorem of Piola allows you to write cardinal equations also for deformable bodies. Okay. So now imagine that instead of giving you that exercise, I give you this other exercise. I have a force distributed per unit line on your beam. So you could say that you are unhappy because you must, in order to calculate the resultant force of the BL, so the resultant of BL is the integral between 0 and L of BL over dx. So you must calculate this integral. If B is constant, this integral is trivial. So somebody learns by heart that I can replace this force, external force, with an equivalent concentrated force, which is placed in exactly that point where the moment of F equivalent is exactly the same as the moment of the distributed force. Okay, so we say that this concentrated force at a certain length, L star, has exactly the same resultant and the same resultant moment as this distributed force. Okay, I have 3 minutes for telling you a nice story when I began my career, the professor with whom I was working, his name is Antonio Di Carlo, was examining with me a student, whom now I met in another situation. And the student was solving this problem for the beam, even when Di Carlo asked him the deformation of the beam. So now you must understand the point. If I ask you to calculate the resultant, the constraint forces, then you can use this external force or this external force as you like. Because the resultant and the resultant moment, the resultant force and the resultant moment are the same. So you write the cardinal equations and you get the same result. So if you want to calculate reactions, you can replace 1 with 2. But if you want to calculate deformations, then there is a difference. Now is the nice story. The student solved this problem too, also for calculating the deformation, and found the wrong result. So the professor told him, look, you are wrong. The student said, professor, they are equivalent. Of course, equivalence, you should say equivalence for what? Okay, equivalence for what? So at the end, Di Carlo went to the blackboard and drew this system of forces equivalent. This is equivalent to 0. Because if these two are equal and with equal intensity but opposite direction, and these two are equivalent to 0, the moment of this pair of forces is 0. So this system is equivalent to 0. Then Di Carlo has drawn this nice picture. So this is a small man, and here are horses. This is a kind of killing used during Middle Ages, you know? So he said to these people, are you happy to stay there? And he said, no. The answer, the next question was, why you are not happy? The forces applied to you are equivalent to 0. And the student saved himself with the answer, I am not a rigid body. Okay? So I hope that telling you this story, I am teaching you that cardinal equations of dynamics are not equivalent to equilibrium for rigid bodies, for deformable bodies. Okay, so you cannot limit your analysis to the cardinal equations. Okay, so we can stop, I think, now.